Hello everybody, welcome. Let's have a look at these past paper questions dealing with calculus. Alright, start with question 1. Consider the function f of x equals x squared minus 3 over x, where x does not equal 0. And the first question they're asking us to find f prime of x. And this prime tells us that we want to find the derivative of f of x. So how do we find f prime of x? How do we find the derivative? We have in our formula booklet this right here. They tell us if we have some function f of x and it's just some general term, let's just say it's some x raised to the power of n. If we take the derivative of this, f prime of x, what we're doing is we're grabbing the exponent, multiplying it out in front, so now it becomes n times x. And this n, which used to be our exponent, and we've multiplied it out in front, we decrease it by 1. That's our derivative formula, and it's in, I'll bring it up actually, it's in our formula booklet right at the very end, topic 5, calculus, right here. That's exactly what they're saying. Some term, x raised to the power of n, what do? Multiply it out in front and then decrease it by 1. Okay, so let's go back to the document and see if we can work out the derivative. I guess just looking at this is a pretty common kind of question that the IB often provides. They'll put a variable, in this case an x, in the denominator. That's at the bottom of a fraction. And if we look at our actual formula, everything is just on one level, for example. Doesn't mean that we can't have fractions, but it means that our variables can't be in the denominator. We need to express them just to an exponent, some power, but they can't be at the bottom of a fraction. So we're going to need to work with this negative 3 over x. So let's go ahead and deal with just this 3 over x for a second. I'm going to write out the function. F of x is equal to x squared minus 3 over x. And let's look at this negative 3 over x for a second. So this negative 3 over x, actually let's just keep it as 3 over x. Let's leave the negative out for a second. This 3 over x is equal to, actually let's keep the negative. Negative 3 over x. This is the same as negative 3 times 1 over x. And the question is, okay, well, what do we do with this 1 over x? Maybe remember this, but notationally, 1 over x is the same as x to the negative 1. And then further on, if we had a different question, 1 over x squared, this would be x to the negative 2, or 1 over x to any power, the nth power, would just be x to the power of negative n. So a general kind of hint, or kind of trick I suppose in some ways, if you have some, let's say some term, and it's let's say 5 over x squared, and you want to write it in an equivalent form where there's no variable in the denominator, you can just keep whatever value is on top, and then just bring up this whole x squared, or whatever it happens to be, but replace the power, that is to say the exponent, just put a negative in front. So if we had, let's say, I don't know, 12 over x cubed, we could bring that up and write 12x to the negative 3, for example. And that would be fine. Okay, and maybe I'll just do one more. Let's say we had 2 over 3x squared, something like this. We can keep this 2/3 times, 2/3 times 1 over x squared, and we know that this would be 2/3 times, well, x to the negative 2. So following along, I'll get a different color, following along on this idea that 1 over x raised to any power just becomes x to the negative of that power. We can use this general structure to rewrite, and we're going to need to rewrite our function before we can take the derivative of it. So let's rewrite this function, and then we can take the derivative. F of x is equal to x squared, x squared minus, and then let's use that strategy. Let's keep this negative 3 here, and let's bring up this x. X used to be raised to the power of 1, and now it's negative 1. Okay, now we have everything we need to take the derivative. That's at f prime. And let's go ahead and use this formula right here. So let's multiply this exponent, this 2 out in front. Then we have 2x, used to be squared, used to be to the power of 2, now it's 1. We don't really need the 1, so let's leave it. And then following along, we have this -1 power. Let's multiply it out in front. -1 times -3 is going to give us +3. And x used to be raised to the power of -1. Let's take 1 away from that, and now it's going to be x to the -2. And that's our derivative. Okay, that was the first part of this question. The next part, they're telling us there's some line L, and it's tangent to f of x at the point 1, -2. Just kind of reminder of what tangent means. Tangent means that if we have some function, let's say like this, and it's at some point right here, if we're looking at a tangent line, we're looking at a line that just touches the function just barely. Essentially, it's the slope of a line at a given point. So that would be one tangent line. If we wanted to find the tangent line here, let's use, be the same color, I suppose. The tangent line would be the slope of the line at a given point. And it doesn't need to be positive. It can also be negative and so on. But when we're talking about tangent, we're talking about the slope of a line at a given point. So they're asking us to find a tangent to f of x at this specific point, 1, -2. So how could we possibly do that? So this is exactly what our derivative or our slope function does for us. So this is our derivative, but it's also called the slope function. And what that means is that, like any function, you can put in some value, some input, and it'll generate some output. So here we can replace x with some value, and what the derivative or the slope function will do for us is it'll tell us the slope of the function at that particular point. So for example, if we wanted to find the slope of the function right here, we could put that value into our derivative. Let's say this is x is equal to 3. We put x is equal to 3 into our derivative, our slope function once again, and out would come, who knows, maybe a value of, I don't know, m is equal to 5 or something like that. And let's say we had this other point right here where x is equal to 1. We put in 1 into our slope function, so just put a 1 in here, replace all the x's with 1, and it would maybe give us a value of m, m is equal to -2. And that's what our derivative does for us. It tells us the slope of a line at a given point, or, not to throw too much terminology, the tangent line, the line which just touches a function at one specific point at that exact point, and it shows you the slope, the rate of increase at that given point. That's our tangent line. So here, they're asking us to find a tangent line at this point 1, -2. Our functions, usually our inputs for our functions, actually always our inputs for our functions, if it's just in terms of f of x, it's just going to be x. So we're really only concerned about this x here. So let's look at our slope function. F prime of x is equal to 2x plus 3x to the -2. And let's input this value of 1. If we input this value of 1 into our slope function, or our derivative, it's going to tell us the slope of a line at that given point. So there we have it. We put in 1 into our derivative, or our slope function, and it'll tell us the slope of a line at that given point. And the slope of a line at a given point is just the tangent line. They mean kind of the same thing. This right here is essentially the tangent, and it's also the slope at a given point. So f prime of 1 is equal to, you can work this out on your calculator, is going to be 5. Not to circle around the point too much, but essentially what we're saying is when x is equal to 1, the slope of this function, or its rate of increase at this specific point, is equal to 5. Okay. Determine the number of lines parallel to L that are tangent to f of x. Justify your answer. So this is kind of like an abstract question. More recent questions are sometimes actually more contextualized, so more real-world situations, but this isn't an impossible question. Determine the number of lines parallel to L, so parallel to this line right here, this L, that are tangent to f of x. Justify your answer. Number of lines parallel to L that are tangent to f of x. So what's going on here, and how can we possibly solve this? What are they actually asking? Let's say we have some function. This isn't the function above. It's not this function in particular, but if we have some function, for example, and let's say it looks like this. I'm going to draw some kind of cubic function. Maybe I'll change it just a little. So let's say we have some function like this. And we've found, let's say, this point when x is equal to 1 and y is equal to -2. So, sorry, let me just change this once more. So x is equal to 1, y is equal to -2. Let's imagine it's right here. 1, -2. And we found the slope of this tangent line. And we said, okay, well, the slope is equal to 5. What they're asking is, okay, well, how many lines are there that are parallel to this L? Right, this is L right here. And the question is, okay, well, how many different points are there on this line that are also going to have, in this case, a slope of 5? How many different points are there on this function where the rate of increase at any given point is equal to 5, where the slope is equal to 5? So how could we do that? So our derivative itself is our slope function, right? And like any function, it accepts inputs, and you put in some input, and then you get some output. So in this case, we put in an input of 1, and the output was 5, which told us that at this point 1, -2 in this case, the slope was equal to 5. So functions accept inputs and outputs. We input some value x, and we get some slope 5. Here, what they're saying is, okay, well, how many points on the line are there, or how many points are there on this function where the slope is equal to 5, where the slope is equal to 5? So in this case, we know our output. We know the slope has to be 5, but the question is, okay, well, how many different x's are there that we can substitute that will make the slope equal to 5? So here, once again, is our slope function. F of x is equal to 2x plus 3x to the -2. And in this case, we don't want to put in an x, an input. We want the slope. We want f prime of x, which is equal to m, right? That's exactly what it is. It's a slope function. We want m to be equal to 5. So essentially, we want f prime of x to be equal to 5. So let's replace this with a 5. And now we have 2x plus 3x to the -2. And to circle around the point too much again, we're saying, what are the x values? How many different x values are there that we can substitute that will make the slope equal to 5? Alright, so in this case we wouldn't want to end-solve this exactly, because it would just give us one value. End-solve would just give us one value. And we want to know the number of lines that are parallel to L. So in this case, I think we'd be best off graphing it. So let's go to the calculator, put in our derivative. So here is our derivative, 2x plus 3x to the -2. That's our derivative. So at any given point, it tells us the slope. And we want to say, okay, well, how many different values are there? How many times does this slope function equal a value of 5? So let's graph another function. And we know that there are 1, 2, and then 3 different points in which we have a slope of 5. Or we can say 3 different times in which this 2x plus 3x to the -2 is equal to 5. Right, so determine the number of lines parallel to L that are tangent to f of x. Going back to the document here, we could say 3 lines, but we would usually want a little more process, so let's go ahead And if you have a graphical solution, it's best to provide at least a sketch. In this case, just looking at the calculator screen, just a little here, something like this, and then something like this. And we have another line just going through. And then we could search 1, 2, 3 points. That might be enough. I'm actually just going to find those values and place them on this function right here, or on this sketch. Would you need to do this for process marks? I think the sketch itself is actually okay. 6.86, and then this is of course 5. This one right here is 1.5, and this final point right here is 2.19 and 5. I'm tempted to bring up the mark scheme, and to be honest, actually I think I will. Let's have a look at the mark scheme. Just bear with me for 1 sec. Or you can skip ahead, I suppose, of course. Okay, so here it is. Here are our solutions, and here it is. Y is f prime of x, so here's our derivative, and then y is equal to 5. So 1, 2, 3 points. 3 points of intersection marked on the graph, that's answer. And then of course there are 3 lines. So sketch is method, 3 points of intersection is one of the answer marks, and then of course stating 3 lines. Alright. Okay, let's go back to the document then.